So let's kick off, Jean-Pierre. Thank you so much for accepting, the invitation for giving the talk in our research center here in Abu Dhabi, in TEI, within TEI. And I will start by introducing Professor Jean-Pierre Hubaux. So through his career, Professor Jean-Pierre Hubaux contributes to laying the foundations and developing the tools for protecting privacy in today's hyper-connected world. He has pioneered the areas of privacy and security in mobile wireless networks and in personalized health. He is the academic director of the EPFL, École Polytechnique Fédérale de Lausanne, which is in Switzerland. So he is the director, academic director of EPFL Center for Digital Trust, C4DT. Until December 2021, he led the Data Protection in Personalized Health project funded by the ETH Council and was co-chair of the Data Security Work Stream of the Global Alliance for Genomics and Health. He is a fellow of both IEEE and ACM since more than 10 years. So recent awards, he got like several awards, and the rest ones he got. So he got, 3 of his papers obtained, distinctions at the IEEE Symposium on Security and Privacy, one of the prestigious conferences in security, 3 times in 2015, 2018, and 2021. And Professor Hubaux, he is among the most cited researchers in privacy protection and in information security. He is a co-author of Tune Insight SA. So thank you so much, Jean-Pierre, for accepting this invitation. And the talk is yours.
Okay, thank you. Thank you so much for the friendly invitation. I just ask maybe whether the audience can hear me well. If you want to put some message on the chat, is it okay? Yeah. So I should go ahead.
So the idea that if they have any questions, they put them in the chat, and then by the end, I can ask you the relevant questions pertaining to the presentation. Yeah.
Very good.
So I think they are writing. Yes, I think I got some messages confirmed. Yeah, it works fine. Yeah. Thank you. You can kick off, Jean-Pierre.
Okay, thank you very much. So it's a pleasure to be at least virtually here in Abu Dhabi. So we're going to talk about truly privacy preserving federated analytics for precision medicine with multi-party homomorphic encryption. I'm going to define also what this means. So the way we started is from this problem statement. So here you see a map of Switzerland. And the question was, how can we explore the data, how we can explore and analyze medical data that happens to be in silos? Because as you know, for medical data, there are very strict regulations, and it is by default prohibited to transfer this data. So the first question was how to explore. So how do we know how many patients in a set of hospitals respond to specific criteria, and then how to analyze these data. And of course, ultimate goal is to improve medical care and to make progress on medical research. So we started with 3 hospitals in Geneva, Lausanne, and Bern. This was 5 years ago. So we leveraged from day one on so-called privacy-enhancing technologies. So, and for this, I need to introduce a few ones. Then there is, of course, traditional symmetric and asymmetric encryption that is, I guess, known to all of you. But there is also more advanced versions of cryptography, homomorphic encryption, and secure multi-party computation. And then there are hardware solutions based on trusted execution environment, and also a technique called differential privacy that leverages on the statistical properties of the outcomes. And there are 2 related techniques, federated learning and synthetic data. Federated learning, I'm going to come back to it. Synthetic data exists. We don't make use of it, and this is a technique that provides dubious protection. So let me give you an example of secure multi-party computation, one of the techniques that I just mentioned. Here the idea is to enable parties to compute collectively a given result. So assume each of the parties here has an input. So the inputs are named x1 to x5, and they want to compute an outcome, a function, based on these inputs, right? And the outcome, as mentioned here, is going to be called y1 to yn. These y values can be the same or can be different. Now, the input, you have to think about it as being potentially a scalar, but it can also be a vector. It can also be a matrix. It can be actually any input on which a function can be computed. And so we want privacy. We understand that the computations are carried out without any of the parties learning the input of the other party. And of course, the output has to be correct. Right? And this is realized by multi-party cryptographic protocol, such that the protocol is run among them. There's no trusted third party. And at the end, each of them receives the output that it is entitled to receive. Now, let me explain this simple this conceptually simple technique on one example, which is assuming there are here 5 people and they want to compute their aggregate wealth, right? They want to know the sum of their wealth, right? So each of the X something here represents the wealth of each individual. And so in order to do so, just for you to get a better feeling of what, get an intuition of what this is about, I'm going to show you a simple way to do this. Simple way is that the first player is going to take, one of the players is going to generate a random number that is way, way bigger, orders of magnitude bigger than the values of X, right? Then this player is going to add this random number with his own wealth and send it to the next player, who will do the same, and so on. So they will add and add and add their own wealth, which means that at the end, what the initiator will receive is a value that is equal to the random value plus the sum of the wealth. What he needs to do is to remove the random number, he knows the random number, and then multicast the outcome to the other players. Right? And so in this way, everyone knows the sum of the wealth without any of them knowing the wealth of any of the other ones. De facto, this works. However, it's a very weak, a very brittle protocol in the sense that, for example, if these 2 players collude and combine the values they have access to, x3 and x1, they can easily single out the value of the value x2 just by computing the difference between m2 and m1, as you can easily check, right? So this shows that naive solutions don't work. So designing robust protocols to achieve what I just mentioned is challenging and requires expertise. A related topic, let's say, operation in addition to secure multi-party computation is homomorphic encryption. So what homomorphic encryption does is that it takes 2 values, A and B, and 2 values A and B. If 2 values A and B, these 2 values, the 2 operands, can be separately, let's say, a function can be computed on the 2 of them, and then there can be an encryption on the outcome. Or there can be first an encryption of each of the operands, and then a computation on the encrypted values. If it is the case that going one way or the other way leads to the same result, then the crypto system is said to be homomorphic. And this is a technique, as is also the case for SMC, that has been known for decades. It is mathematically proven. However, the, let's say, usability in real life was not available yet until recently because performance was very poor. So a number of libraries have been developed over the last years in order to support this kind of, let's say, schemes, or let's say homomorphic encryption scheme. And one of them is Latigo. This is something that has been developed in my lab. It's called Latigo because it's based on lattice-based crypto, and it is programmed in the Go language. So this is something that is fully operational and open source that you can play with whenever you wish. So now to come back to the question of medical data, what we have done here is to deploy a system based on the techniques that I've just described that works in the following way. So assume there are three hospitals. Each of them has to be perceived as a data provider, right? So each of the way the system works is that it elaborates. Now I'm referring to machine learning. What we want to do is to elaborate a machine learning model that captures the information provided by these three data sets without merging the data sets, right? And so in order to do this efficiently, the best way that we have found is to compute the gradients locally, and each of them, and then to once the local computations have been carried out, the outcomes are encrypted homomorphically, and the better model is elaborated based on the partial contributions of each of the data providers. And the reason to encrypt this homomorphically is that it is the best technique to protect against information leakage that would otherwise happen by providing the partial aggregates in clear text. Okay. So I hope this is clear. Let me know in the chat if you have problems to understand these concepts. Now, if we have developed this, we've deployed it already in the three mentioned hospitals. And this is the feedback we received from the head of precision oncology from the Lausanne University Hospital, who expresses a deep satisfaction with this approach because he understood this was a way to solve the problem of data sharing in medicine, and in this specific case in oncology. So we publish this in, well, usually we publish in computer science conferences, but to explain this to the users community, we publish this in Nature Communications actually in October, a year ago actually. And we publish this in collaboration with our colleagues at Lausanne University Hospital, and also there were also two Boston colleagues, one from MIT and one from the Broad Institute, who joined this effort. What we have shown in this work is the following. So we took an already existing paper that had been published in 2019 in Nature Genetics that exhibited the following plot. What is shown here on the left-hand side is you have here on the x-axis you have the time in months, and here on the y-axis is the overall survival of patients and different let's say subpopulations of the patients, right? And so this is the kind of data that were computed by putting in that specific study. All their data were available in clear text and were centralized. So, and they developed the model in that framework. What we have shown is what we've done is that we've taken this data set, we've chunked it in three pieces, and shown that we could obtain exactly the same results in spite of the fact that the data were not in the same location, and in spite of the fact that as a consequence we had to do all the computations under fully homomorphic encryption, or more specifically multi-party homomorphic encryption, which means doing what I mentioned before, which means going, if I go back to the scheme, making some of the computations locally, compute partial results. So typically the coefficients of a neural network, and then carrying out an iteration that makes the model even more accurate, right? And so we have done this for, as mentioned here, for survival curves, with a performance that is shown here, where you see here the runtime. The runtime is very, I would say, acceptable. We're talking about a few seconds of computation. Then we've taken another paper that was about genome-wide association studies, or GWAS. For those of you who are not familiar with this, what you see here is the so-called Manhattan plot, which means you see here horizontally the human chromosomes, 22 human chromosomes. And what you see here is a p-value, which means it is the impact of a given variant on a given chromosome for a given condition or for a given predisposition, right? So you see here, for example, chromosome number 6, there is a variance, which means there is a peculiarity in the chromosome that leads to a much higher likelihood, for example, to develop a given disease, right? For example, right? And you see there's another one here. So again, what we did is we took as a starting point an already published paper, again by other researchers, and that had produced this plot. And we have demonstrated that we could obtain the same result after having chunked the data in a certain number of subsets and doing all the operations in the way that I've shown previously. And we also show that if one doesn't do this, so if one tries to do an independent approach or meta-analysis, meta-analysis, or an approach that doesn't, let's say that, for example, that tries to make just averages on the contributions of each of the data providers, one obtains results that are completely erroneous. That's what is really needed to have this ability to do the machine learning computations or elaboration of the model with the techniques that I've mentioned previously. So this is the performance. So this is actually the very big data. We're talking here about billions of data points, as you can see, billions of data points. And the runtime as a consequence was at that time, when we elaborated the paper, in the order of thousands of minutes. De facto, we have worked extensively in order to bring improvements to the whole thing. And so the commercial version of the software is around 2 orders of magnitudes faster. You have to divide by roughly 100 to have the current values nowadays. Then we've looked extensively at the issues of compliance. So we have worked also with, as a consequence, with lawyers, ethicists, in order to position, let's say, the techniques that I mentioned previously, vis-a-vis, to position them vis-a-vis GDPR, right? So GDPR, I trust you are familiar with this. So the general data protection regulations that are enforced in the EU since May 2018. So in this framework, we have written something called a DPIA, a data protection impact assessment, that assesses what are the risks before deploying these kind of tools. I won't go through all the details, it would take too much time, but just going through, you can see what this means. This was the situation before, and this is a situation after. And as you can guess, red is not good, green is good. Of course, what is the DPIA is not written like this. DPIA is a thick document, relatively boring, that goes through all the things, but it's boring, but it's important. It's very important because this is what lawyers have to read in order to provide their green light for the deployment of a given tool. And as you can imagine, in Swiss university hospitals, they look very, very carefully at what you do. So we had this analyzed by the federal authorities of data protection. So here is the head of the data protection authority at the federal level, who has provided a green light, and so that essentially has enabled us to move on with further deployment. We have also applied this to single cell analysis. Now, for the sake of time, to leave enough time for questions, I'm going to skip this thing, but I can go back if you have a specific interest. Otherwise, the paper is about this is online as well. What we've seen is that actually this technique that we initially applied to the health sector is actually applicable also in other application verticals, including insurance and cyber intelligence. So we have developed in this framework a project with a Swiss Re, a big reinsurance company in Switzerland, and the cyber intelligence project with AMA Swiss, which is the research branch of the Swiss military. Based on this success, we said, oh, well, there is enough application here. Why don't we commercialize the whole thing? So we have created a startup company called Tune Insight that provide the support for secure data collaborations, exactly along the lines of what we have seen before. So this is what it does. So what we have done in this framework is to industrialize notably the health care sector solution with the deployment guide of the whole thing, and then the whole stuff. Okay, there may be more, let's say, details. We also made an IT security assessment. I mean, to deploy software in hospitals here, you have to really you have to be super cautious and check absolutely everything. And this is the current status of the pilots. So we have for two application projects, one in oncology and another one for the computation of biological references. We have a deployment that is in Geneva, in Lausanne, in Bern, and in Zurich. So we get a bit of Swiss geography here. So, and this is in each case, it means that Tune Insight software is installed at their premises and runs there. So it does not, for the moment, it's not a cloud version. They really wanted to have something that is fully decentralized. Now, before concluding, I like to emphasize the fact that to give you an idea of what the landscape looks like. Voilà, so starting here from this big bubble, in order to share without sharing, right? If you want to share without sharing, which means you want to elaborate a machine learning model without centralizing the data, right? So you keep the data in silos. You have several options. This is a kind of decision tree. So one option is to go for a hardware solution. Hardware solution means you make use of a trusted execution environment, centralize the data there in the enclave, make the computation there, and provide the results. This is a solution that is a kind of short-term solution, but it has multiple drawbacks. In particular, it requires to trust the vendor of these devices, and it is vulnerable to side channel attacks, as has been shown by many researchers. Then if you don't want to go hardware, you go software. Software, one solution is to go to something that we like to call vanilla federated learning, which means you do your computations locally in each silo, and then in clear text, you aggregate the whole thing. But by doing so, it is well known, and there are many papers that have shown that you open the door to a number of vulnerabilities because you expose actually partial aggregates. So this is not good either. So you have to protect partial aggregates. And this you can do in two ways. Either you add noise or you do it by crypto. If you add noise, you do it typically by making use of differential privacies that I mentioned previously. But the drawback here is by doing so, you reduce the quality of the data. And so this is something that usually end users don't like. So then one has to go by crypto. And by crypto, there are two options: either make use of homomorphic encryption or secure multi-party computation. If you make use only of secure multi-party computation, then the drawback is that performance is very disappointing because you have to push around a huge amount of data. If you make use of only homomorphic encryption, then you are limited to just 2 parties. So in order to have the ability to go to more than 2 parties and to be able to have reasonable performance, then you have to combine secure multi-party computation and homomorphic encryption, which is what is called multi-party homomorphic encryption. And this is exactly what the company TuneInsight does. So to conclude, so what we've done is to streamline the solution to the problem of privacy-preserving federated analytics. Switzerland being a federal country, we have all the complexity, if you wish, of almost all the complexity of an international setting because of the federalistic legal system and ethical system, which led us to develop this solution, which is a kind of prototype, if you wish, to work at the international scale. Clearly, as mentioned, university hospitals are very cautious when it comes to data sharing, and the solution that we've deployed solves the above-mentioned issues. We also worked on the international outreach in the sense that, we have published this thing extensively, and we are in touch with many end users also abroad. What was crucial for the long-term success of this endeavor, because this endeavor was initially a purely academic endeavor, what was crucial was to make sure that we would be able to provide customer care, and making customer care was possible only by incorporating a company that then takes care of all the nitty-gritty issues related to deployment in real settings and so on. So this was the main motivation to incorporate a year ago the company TuneInsight that I mentioned previously. Well, so I thank you for your kind attention and would be happy to respond to questions.
Thank you so much, Jean-Pierre, for this nice presentation and for this nice talk. I have one question. Here, on what you presented, we can observe, of course, that the main cost of such solutions, in the network load, and of course, setting up such kind of solution, it's quite big in terms of, the generation of evaluation keys. So here, for instance, for the rotation operations, is there any platform that considers, this fact in terms of consumption of resources? Because for such scenarios with a single evaluation of a circuits, with few multiplication gates and a small number of input parties, this may be not be possible to deploy them. Have you studied these aspects in terms of computations?
Yeah, so we've worked extensively on the performance of the whole thing to make sure that the computation effort would be reasonable. And de facto, if I go back to the solution, right, what is crucial to realize is that we much of the computation is actually carried out in clear text. If we go back to the thing here, as you can see here, there is at each data provider there is substantial work that is done on the local data, right? And this is done in clear text, so this goes very fast, right? So it is what is extracted from there is just tiny subset, let's say an amount of data that is way smaller than the data that are processed at the data provider in clear text, right? And by doing so, we have, let's say, the performance issue has become a non-issue. I would say this is really something that is that is completely now in the background. The deployment issue that we face for, let's say, in real world applications are more related to the quality of the data, to the homogeneity of the data, and to the integration in the data flows of the customers, right? Because this is something that they are not used to. And so it has to fit, right, in the things that they do. And an additional issue, I would say, is that most people we talk with who are actually decision makers to deploy these kind of solutions are not computer scientists, right? They are managers, they are the background that is, in business or in law or whatever. So when we talk to them about, doing computations under homomorphic encryption, they have a hard time really understanding what this means, right? And these are smart people, so they are unwilling to, they want to understand by themselves, right? And so these are typically the obstacles we are facing. But I would say the performance aspects and so on, we consider them to be solved. If this were the only problem, then we would be, then the company would thrive.
Yeah, I see. And a second question regarding, here we're talking about the performance, but also it's quite correlated to an efficient communication across the federated network. Is there any issues in terms of managing the heterogeneity of systems, within the same network?
Yeah, absolutely. So absolutely. So this is where, as soon as you go to the real world, then you hit all the questions you are, I think, alluding to. So, for example, there might be firewalls, right? That might come in your way and complicate stories. The ports you are given access to, the restrictions in what you are allowed to install, the chronic overload of the CISOs, right? The Chief Information Security Officers you have to deal with, right? You have to cope with these people because they have to provide green light, they have to provide you access to their servers. And then the understanding of the DPOs, or data protection officers. CISOs are typically, IT people, so techies, whereas the DPOs are more often than not are lawyers. Completely different crowd, completely different mindset. But you have to have both of them with you, right? Because if any of the two says, well, I'm unhappy with what you are telling me, or we don't have the time, well, you're doomed, right? So it is this diversity of, plus of course, the end users, right? And so because neither the CISO nor the DPO are pushing for this because they are not users, right? They are just enablers. So you have to convince the users there. And usually you have to deal with the upper management of the company, right? Because they say, well, what are you doing here? Well, what are you talking about, right? So you have to go relatively high in the decision ladders in order to obtain green light, right? So typically these are obstacles that are to be in some way addressed. And also the fact that we are talking here about techniques that are relatively recent in terms of their, as I mentioned, they are decades old, right? These tricks have been known for 40 years, theoretically, right? Fundamentally, but in terms of real deployment, we are talking about things that are being deployed as we speak, right? As a consequence, the standards and the practice and everything about mature technology is not there yet, right? So there is a lot of try and error and talking with people and so on, and by its nature, as we're talking about here about something that is federated, you have to deal with multiple organizations, or at least with multiple subsidiaries within the same organization, right? A typical application scenario would be the same company that is operating in different countries and that is not allowed to bring all its own data together. This happens actually more often than we thought initially. But nevertheless, right, you have to deal with the local people, with local mindsets, regulations, languages, and so on. So it's an interesting challenge.
Good. Thank you so much. Very well seen, Professor Jean-Pierre. I think it's fine today from our side. I would like to thank you again, Jean-Pierre. Yeah, and okay, so well, let's keep in touch. So I would like to thank you again for the quality, for the benefits, because as you mentioned, we do have several use cases that could be applied on such approaches, and thank you again. Yeah,
my pleasure. Okay, take care and have a nice afternoon. Yeah, take care.
Thank
Bye.
you so much.
Bye.
Thank you. Bye bye.